Welcome back to this next video in which we are discussing modular arithmetic. Okay, so we've now seen that modular arithmetic is all about these ring number systems that you can construct by quotienting out the ring of integers by an ideal of the ring of integers, which is something of the form n times z. Okay, so what we now want to actually do is construct these quotient rings. And remember, to construct a quotient ring, what we need to do firstly is divide the set that underlies the initial ring up into the cosets of the ideal. Okay, so that's what we're going to start off by doing. Now, I'm about to draw a picture for this, and the picture will be relevant for all ideals except for one. And the one ideal it won't be relevant for is the 0 ideal, okay, where n is 0 here. Okay, but that's okay because we know, we understand what we'll get if we quotient out the ring of integers by the 0 ideal. Whenever you quotient any ring out by the 0 ideal, you just end up with something that's isomorphic to the initial ring back again. We discussed that in the video on quotient rings. So if we quotient out by the 0 ideal, we'll just end up with the integers back again. Okay, so the picture I'm about to draw will apply for any other ideal of this form n times z, except when n is equal to 0. Okay, so let's firstly then start by constructing the actual set that is going to be our modular arithmetic ring number system then. Okay, and we're going to do this by splitting up our ring of integers into the cosets of the ideal here. Okay, so to get some intuition for this then, I'm going to draw a number line for the ring of integers here, and I'm going to plot on this n times z, just like we did before. Okay, so all integer multiples of n then are going to look like this. You'll have 0, you'll have n, you'll have negative n, you'll have 2n, and I'll add 3n on there as well, and then you'll have negative 2n here, and then negative 3n here, and it will go on and on and on, of course. Okay, so here are integer multiples of n. So here are the elements of our ideal here plotted on the number line. So I will just colour this in. So this is n times z, or the principal ideal generated by n, and this is the reason I had to say we're excluding the 0 ideal from this, because of course the 0 ideal would just contain the point 0, so it wouldn't be this beautiful lattice, it would just contain 1 point. Okay, but for all other n, it will look like this. Okay, so now what we're going to do then is we're going to form the additive cosets of this ideal within the ring of integers, and those additive cosets then, those are going to be the elements of our new quotient ring. Okay, so what are the additive cosets of this going to be? Well, of course, what we need to do is we need to take elements that are outside of this ideal here, and then add all the elements of the ideal here onto that element. So for instance, if we look at the element 1, which looks to be outside of this, of course you have to think carefully about this, because if of course this n was equal to 1, then our ideal would be the entire ring, and then there would be nothing outside of it. But for n is greater than 1, of course 1 will be outside of the ideal here. Okay, so what we can then do is generate the coset of the ideal under the element 1, and what that will involve doing is adding 1 onto all of the elements of the ideal, basically. So what you'll want to do is add on to n here 1 to get n plus 1, add on to 2n here 1 to get 2n plus 1, again for 3n plus 1, 1 onto negative n to get negative n plus 1, 1 onto negative 2n to get negative 2n plus 1, and 1 onto negative 3n to get negative 3n plus 1, and etc, etc for the entire number line, okay, for the entire integers. And here then is this coset of the ideal nz here under the element 1. So there is a coset, or an equivalence class, or a residue, whatever you want to call it. Okay, and of course this will continue on. You can do this for 2, 3, all the way up to right down here. Okay, so you'll have n minus 1 here, okay, the integer that's right to the left of n here, and of course you can generate its coset, and that will be all of the elements that are just to the left of the green dots here, like so. Okay, so it's n minus 1 plus all of the green dots, which will take you up to the point just to the left of the next one along. Okay, so if I just show all of these on here, and I think I'll colour that in orange here. So here is another coset. Okay, so you will overall end up then with n minus 1 of these cosets in this way. Okay, now the first thing to do then is give these cosets names. We will use the normal notation for giving cosets names, and the way that you name cosets normally is you take a representative from each coset and then you put a bar over it. So for our green coset, we need to pick a representative, and the most obvious representative to choose is 0. That's the most special element that that coset contains. So we'll then call this entire coset 0 bar. So 0 bar refers to the entire coset of the ideal in the ring of integers which contains 0. Okay, then of course we'll have the red coset here, which its most notable element, but of course you could choose another element, but its most notable element is 1 here, so we'll call it 1 bar. Okay, so I'll underline that in red, so we'll call the red coset 1 bar. You'd then have 2 bar, 3 bar, 4 bar, all the way up to n minus 1 bar, which would be the orange coset here. Its most notable element is n minus 1 there. Okay, so this is what we're going to call all of these cosets of the ideals here. Okay, we're going to name them by which element they contain that is between 0 and n here. Okay, so we're looking just at this little portion here. But of course you could name them according to other representatives, it's just those are the easiest representatives to work with. Okay, so then, to actually construct this quotient ring then, Z mod NZ, the modular arithmetic ring structure here, you're going to then put these cosets into a set. So you'll have 0 bar, 1 bar, all the way along to n minus 1 bar. Okay, so all of the cosets of the ideal go into a set, and these are going to be the elements of our new algebraic number system here, our modular arithmetic number system. So we've got 0 bar, 1 bar, 2 bar, all the way up to n minus 1 bar. And of course, how many elements you have will depend on which n you chose, so which ideal you actually chose to quotient out by to form the modular arithmetic. So there are many different number systems which are all counted as modular arithmetic. Okay, and then it's just normal quotient ring stuff. We define addition and multiplication on this set of cosets in exactly the same way as we define addition and multiplication in an arbitrary quotient ring. Okay, so if I have two cosets here, A bar and let's say B bar, and I want to know how do you add these together. Okay, so in this new number system that I'm forming here, Z mod NZ, how do you add these two cosets together? Well, the way you do it is you use addition on the ring of integers. So you say, okay, take a representative from this coset, take a representative from this coset, add those two representatives together in the ring of integers, and you can pick whichever cosets you like. Okay, so red plus means plus in the quotient ring here. Green plus means plus in the initial integers. So you add A and B, which are two representatives of A bar and B bar. They're the most obvious representatives to choose because they're the representatives that the entire cosets are named after. And then take the coset that contains that. Okay, and we know from our study of quotient rings previously in this playlist on ring theory that this way of defining addition is firstly well defined, so that means it does not matter which representatives you pick here, the coset that you get as the answer will always be the same. And it also obeys the axioms of an abelian group operation, provided that, of course, you start off with an initial ring in which the addition law obeys the axioms of an abelian group. Okay, which indeed certainly the integers is. And then the way that we define multiplication is exactly the same. So if we want to know what A bar multiplied by B bar is, where this is multiplication in our quotient ring here, the way that you do it is you take a representative from each of them. So we can take the representative A from A bar, we can take the representative B from B bar, you multiply them together in the ring of integers again. Okay, so multiply the two representatives together in the integers and then ask, well, which coset is A times B actually in? So you take A times B bar here. Okay, and again, in the video on quotient rings, we proved for an arbitrary for an arbitrary quotient ring that you're working with, that this is a well-defined multiplication law. Okay, so it does not matter which representative you take from these two cosets, you'll always get the same coset as your answer here. And we also proved that it obeys the necessary axioms of a commutative ring. Okay, that's how we're going to define addition and multiplication on this quotient ring Z mod nz in the normal way that we do on quotient rings. Okay, so now what I want to do is, I'm not going to go through all of what we prove in the video on quotient rings because it takes a long time, and you can just watch that more general video to understand that. What I do just want to do is give you some examples of working with modular arithmetic and how you can think of it working, and also give you a bit more nomenclature or terminology or notation, okay, because there is old notation for how people denote this. Okay, so firstly, actually a bit more nomenclature. So people don't usually refer to these as the cosets when they're working in modular arithmetic. And by the way, this is modular arithmetic here. This is modular arithmetic modulo n. Okay, so you choose your little n here, and then if someone talks about modular arithmetic modulo n, so they give you some little n which is a greater than or equal to 0 integer here, and they tell you to do modular arithmetic modulo n, it means working in this number system here. Okay, however, people don't usually refer to the cosets. The bar notation is standard, so people will write 0 bar, 1 bar, all the way up to n minus 1 bar, but they don't usually refer to them as cosets. Instead, they refer to them as either equivalence classes, or residues, or also congruence classes. Okay, and that's the new one. Okay, so equivalence classes and residues, they can be used in the arbitrary ring theory case. However, congruence classes is usually just reserved for modular arithmetic. Okay, so these are also called congruence classes. Okay, so this would be called the congruence class of 0. Okay, so that just means the coset that contains 0, all of these elements of the original ring of integers. This would be called the congruence class of 1, all the way up to the congruence class of n minus 1 here. Okay, so now let's actually do some examples of working with modular arithmetic to get a feel for this. Okay, so let's take, as an arbitrary example, n is equal to 7. So we'll have z mod 7z. Okay, so firstly, let's just think about this as a set. So as a set, this is going to contain 7 equivalence classes, the equivalence class containing 0, the equivalence class containing 1, the equivalence class containing 2, the equivalence class containing 3, the equivalence class containing 4, the equivalence class containing 5, and the equivalence class containing 6, but not the equivalence class containing 7. The equivalence class containing 7 is already in here because that's 0 bar. So if you like, you could rename 0 bar as 7 bar. Okay, it's just more standard to call it 0 bar. Okay, so let's do some examples of adding together things in this number system. Okay, so if I want to add together 4 and let's say 6, okay, if I want to add these two together, how does it work? Well, what you do is you take a representative from both of these equivalence classes. Okay, so you take a representative from 4 bar and the representative from 6 bar, and you can take whatever representatives you like. However, what are the most obvious representatives to take? The most obvious representatives to take are 4 and 6. Okay, and you then add them together in the initial ring of integers. So this is green addition in the initial ring of integers. So normal addition, this is addition of the congruence classes. Okay, so you take 4 plus 6, which of course is equal to 10, and you take the coset that contains 10. Okay, the equivalence class that contains 10. Now, what is the equivalence class that contains 10? Okay, well, obviously, it's not instantly obvious which one that is, but it is going to be one of these. So what coset is 10 in? Which one of these cosets is 10 going to be in? Well, note that I can write 10 as 7 plus 3. Okay, so I can split it into a multiple of 7 plus a remainder that's in between 0 and 6. Okay, and that's exactly what I need to do, because now this means that 10 is going to be in the same coset as 3, because look, I can take 3 and add on a multiple of 7, okay, which is all things in my ideal here, and then I've got 10, so that means that 10 must be in the same coset as 3, the same additive coset as 3. Okay, so the answer here is going to be 3 bar. So in this case, 4 bar plus 6 bar is equal to 3 bar. Okay, so there's an example of how to add these two together, and I just want to show you that if we picked different representatives from these two cosets, we'd have got the exact same answer. We do, as I say, prove that this is well defined in the video on quotient rings, but let's just do an example to show that it's well defined. So let's take another representative from here. So things in this coset are just 4 plus any integer multiple of 7, so why don't we add on 21, 3 times 7? Okay, so then we'll have 25 as our representative from 4 bar. And what about taking a negative number for 6 bar here? Okay, so what about negative 1, which is in the same coset as 6 bar, because of course if we subtract 7 or add on negative 7 here, we'll get negative 1. Okay, so let's add these two together instead. Let's choose these two as our representatives of these cosets, add those two together in the integers, and take their answer. Well, of course, if we add these two together in the integers, we'll get 24, and then we want the coset containing 24 here. Okay, now, is this going to be the same? Well, we better hope it is. It should be 3 bar here. Why is it going to be 3 bar? Well, of course, 24 is equal to 3 times 7, 21, plus 3. Okay, so again, I've expressed it as some multiple of 7 plus a remainder portion, and that remainder portion is 3. Okay, so that means it's going to be in the same additive coset as 3. So this is actually going to equal 3 bar. So indeed, there's a little demonstration of how it's well defined. Okay, right. So that's how we add things together. We add them together, we add two representatives together, and then what we say is, okay, which coset is this in? And to work out which coset it's in, all we need to do is think about writing the answer that we get as some multiple of 7 plus a remainder, where that remainder is between 0 and 6, so that we can get it in terms of one of these cosets here, where we've named the cosets according to these representatives that are in between 0 and 6. Okay, so that's how we add cosets together. Let's think about multiplying cosets together. So let's do 4 bar multiplied with 6 bar, just as an example. Okay, so the way you do this again is you take representatives from both cosets. So you'd say, okay, I need a representative from 4 bar, we might as well take 4. I need a representative from 6 bar, we might as well take 6. We'll multiply them together in the initial integers, get some answer in the initial integers, and just take the equivalence class that contains that. Well, 4 times 6 is 24, so again, we are taking the coset that contains 24, and we've already exactly done that. We know that that will be equal to 3 bar. Okay, so the answer here is that 4 bar times 6 bar is equal to 3 bar. Okay, so hopefully you can see that the arithmetic on these new number systems is very different from arithmetic in the original integers. Okay, 4 bar times 6 bar is equal to 3 bar. Okay, so it is very, very different, and it takes some getting used to. Now, to end then this video, what I just want to do is show you the old notation for how people did this. In my opinion, the best notation is just to do it as I've been doing it here. Put the bars over them to denote the equivalence class, and then just say it's equal to another equivalence class, 3 bar, like so. That's my favourite notation. That's the simplest notation. However, there is old notation that is still very, very commonplace, particularly in things like number theory. Okay, so I want to show you this old notation. So, the old notation that people would have used for this sort of thing. Okay, so this is my favourite notation, just writing 4 bar plus 6 bar is equal to 3 bar, like so. Okay, where of course this means addition in our quotient ring here. But the old notation for this expression would have been that 4, you wouldn't put the bar, you'd put 4 plus 6 is congruent to, so you'd put 3 equals here, is congruent to 3 modulo 7. Okay, this is the old notation for writing this, that if you take 4 plus 6, the answer is in the same congruency class, is congruent to, so this this big equals here with 3 lines should be read as is congruent to free, okay, so is this in the same congruency class as free if we are working modulo 7, okay, so if we're working in Z mod 7Z, okay, so as I say, that notation is still prevalent, especially in things like number theory, and it's the old notation. Okay, equivalently, doing an example for multiplication, if we have 4 bar times 6 bar is equal to 3 bar, my favourite notation here. Okay, in the old notation this would have been 4 times 6, again, is congruent to 3, and then you put in brackets here, modulo 7. So the nice thing about the old notation is that it tells you exactly which modular number system you're working with. It tells you that you're working in Z mod 7Z, where of course this doesn't tell you it. Of course you could write in brackets here modulo 7 as well, okay, so that you know that you are working in Z mod 7Z. Okay, but that is the old notation, and you will see that used. A lot of texts on number theory still use that notation. Okay, but that's all that it means. It just means add 4 bar and 6 bar together in Z mod 7Z and it gives you 3 bar. Okay, and with that we will end this video.